We build giant instruments with gold-plated mirrors to search for life in the deep cosmos. This search is an investigation into our own makeup, as the same chemical elements found in these space telescopes once drifted as dead matter in a primordial sea. 4.5 billion years ago, during the Hadean Eon, Earth was a sphere of boiling magma under a dark sky. The surface was a churning sea of molten rock, with no solid ground and no possibility of spontaneous biological life. Tracing the path from these boiling minerals to a living cell requires identifying the specific point where dead chemistry began to organize, replicate, and persist on this toxic rock. Since the late 19th century, scientists have debated how life arrived on this cooling surface. Svante Arrhenius proposed a theory known as panspermia to explain the arrival of biological seeds. This early hypothesis suggested that living bacteria, trapped inside cosmic debris, survived the vacuum of space to seed the Earth after impact. Modern evidence supports a different variation, called pseudo-panspermia. Rather than carrying living organisms, comets and meteorites delivered the organic building blocks of life, including amino acids and lipid molecules. For millions of years, an intense meteoritic bombardment deposited these chemical ingredients into the young, barren oceans, slowly increasing their concentration in the water. These ingredients were the raw materials for life, but they required a specific environment and a continuous power source to begin the complex reactions necessary for biology. 4 billion years ago, the Archean ocean floor was a pitch-black, iron-rich environment. It was completely anoxic and cut off from the energy of the sun. Standing on this seafloor were alkaline hydrothermal vents, like the Lost City. These massive geological structures functioned as electrochemical flow reactors, persisting for over 100,000 years. This schematic shows the vents' internal mechanics. Highly alkaline fluids mixed with acidic ocean water within a labyrinth of thin, inorganic micropores. As fluids moved through these pores, they created a natural proton gradient across the mineral walls, separating hydrogen and hydroxide ions. This chart compares the ancient vent structure on the left with a modern living cell on the right. Both rely on the same proton motive force to generate energy, suggesting our cellular mechanisms originated in these rock pores. This geological battery provided the continuous energy to force simple organic molecules into organized biological systems. In this environment, lipid molecules from space self-organized into protective bubbles within the vent pores. These membranes trapped the geochemical energy, creating a microenvironment where reactions could accelerate. The result was LUCA, the last universal common ancestor. Reconstructed data depicts LUCA as a heat-loving, anaerobic microbe that lived entirely on the hydrogen and CO2 provided by the vents. This phylogenetic tree shows how LUCA is identified. By tracing 355 protein families common to both bacteria and archaea, scientists can map the physiology of this original biological entity. LUCA's genetic footprint demonstrates that life emerged through a specific, replicable sequence of geochemical events. These early life forms were geographically trapped, entirely dependent on the energy flowing through the vents. Life expanded with oxygenic photosynthesis. This innovation allowed organisms to harvest sunlight directly, enabling them to leave the vents and colonize the open ocean. This success had a toxic consequence. Photosynthesis produces free oxygen as a byproduct, which was lethal to the anaerobic life forms that had dominated the Earth for eons. We see evidence of this in banded iron formations. Oxygen reacted with dissolved iron, creating massive deposits of red hematite on the ocean floor. During the Great Oxidation Event, biological oxygen production outpaced the Earth's natural sinks, causing the gas to accumulate in the atmosphere. This shift destroyed the existing methane greenhouse effect, plunging the Earth into a global ice age and triggering a mass extinction. The Great Oxidation Event was a radical selective pressure, proving that life's most successful survival innovation was also its most significant existential threat. Biological sources and sinks eventually stabilized, and oxygen became a permanent part of the Earth's atmosphere. This chart shows how the spike in atmospheric oxygen provided the metabolic energy needed for the evolution of highly complex multicellular life. Over millions of years, life moved from simple marine cells to massive terrestrial animals, fueled by this high-octane oxygen environment. This energy surplus supported larger brain sizes in mammals, the development of social structures, and the mastery of tools and fire. The environmental volatility of the Earth acted as the exact selective pressure required to forge intelligence. Human civilization is the continuation of that original Archean chemical process. The energy mechanisms in our own cells operate on the same proton gradients that first powered life in the alkaline vents. Every breath we take relies on the oxygen byproduct that once caused a global catastrophe. This 3 billion-year chemical journey has resulted in a biology that builds space telescopes to search for its own origins. The primordial matter of the Hadean Earth is finally exploring the processes that created it.